Right, so we got this tricky differentiation problem where it's asking us to find the stationary points of the curve. So whenever you're thinking stationary points, it should always be dy dx equals 0. So before we approach this problem and solve it, I want to introduce you to the idea of, you see 8 marks on this and you think, oh my god, I can't do this. Oh my god, this is long, this is tough, whatever that. I want you to take that idea and I want you to put it in the bin. And I want you to break it down into smaller chunks that literally a monkey could do, and just do that, because that's just really how simple it is. I mean, if you had the knowledge to do it. Well, yeah. Carrying on. So the knowledge for this, so you need to, first of all, you need to think, okay, you need to find dy by dx, you need to find the gradient function of this equation. So yeah, you need to find the gradient function of this equation, and you need to essentially find the stationary point. So that's when the gradient function equals 0. And that's what you're going to input once you find the gradient function. So yeah, let's begin. So we have this. Okay, this is not a good format in which we want to differentiate this. So we want to implicitly differentiate this. So I'm just going to multiply by y both sides to make this simpler. So that should be 3x squared minus 5y squared equals, well, 2x plus 16 times y. Well, that's just this. Right, now that's a bit better. That's lovely. So we have the we have the equation that we can implicitly differentiate it now. It's in a format we can easily implicitly differentiate. So let's do that. Right. Then if we do that, we get 6x minus 10y dy by dx equals, right, this one we're going to have to use product rule to differentiate. So if we do that, it's this. Right. If we tidy this up, it's going to be, right, now that we have this, there's two routes to which you can take. You can just simply input dy dx equals to 0 and just eliminate these constants right here, which is probably the easier and quicker method, which is something I'm going to do. Or you could, rearrange and, find just rearrange for dy dx, and it's the same thing, but it just takes longer. And I just think that taking a shortcut is always better. So let's just do that. If we do that, we get 6x equals 2y. And yeah, 6x equals 2y, 6x minus 2y equals 0. Okay, now if we go back to the original question, that's basically like the gradient function of this curve. It's not in terms of dy dx, but that's the gradient function of the original equation. So the original equation is, I'm going to pick this format. I think this format is easier to just use. So 3x squared minus 5y squared equals 2xy plus 16y. You 2y equals 6x, y equals 6x over 2, which is 3x. So now that y is equals 3x, you can say, okay, 3x squared minus 5 times 3x squared equals 2x times 3x plus 16 times 3x. So essentially you're just inputting all of the y values in this equation in terms of x that you found. So if we do that, I'm going to write this down here, 3x squared minus 5, 16 times 3 is 30 plus 18, which is 48x. And yeah, that should be what you get. And from that, it's a quadratic. So let's do this. So 45x squared plus 6x squared minus 3x squared plus 48x equals 0. So 45x squared plus 3x squared plus 48x equals 0. 48x squared plus 48x equals 0. Now if we just take the 48 out and the x out, you get x plus 1 equals 0. Or, you know, x squared plus x. Yeah, that's not necessary. So we get x equals minus 1 or x equals 0. That's the x coordinates of the stationary points. And for y, we're almost done. Y equals 3x. So y equals 3 times minus 1. Y equals 3 times 0. So that's minus 3 and 0. Therefore, the stationary points are going to be minus 1, minus 3, and 0, 0. And therefore done. Yeah. That's it. We managed to solve it. It's really not that difficult. I'm surprised this was even 8 marks. So, yeah, this was fun. One thing that I missed out was that y can't equal 0. In the question, it clearly stated y cannot equal 0. So, essentially, this stationary point is invalid, and now we're done. Yeah.